start off section 2.2, I thought I'd give us some fairly easy examples of some of the vocabulary and the symbols. So we're going to treat these as true or false. These are the sets A, B, and C for this example. The first statement, A is a subset of B, means that A is a proper subset of B, means that all the elements in A are in B and the two sets are not equal. Certainly a square is in the set B, and so this is true. C is a proper subset of B. That means all the elements in C are in B, which is true, and C does not equal B, which is false. So this is a false statement. When you use this particular subset symbol, remember, it implies that the two sets are not equal. B is a proper subset of C. That's just as false as the previous one. B equals C. That is a true statement because they have exactly the same elements. A is a subset of B. That means everything in A is in B, and that's true. C is a subset of B. That means everything in C is in B, and that's true. B is a subset of C is true. B does not equal C is false. B equals C, so B cannot not equal C. This says the number of elements in B, the cardinality of B, equals the number of elements in C, the cardinality of C, and that is true. If two sets have the same number of elements, then they are equivalent to each other, so this is true. Next, I'd like to look at the subsets of A, the set A with you, and I've let the set A equal the set that has A, little b, little c in it. So these are the subsets. I've listed them in order of how many elements are in the subset. This one has no elements at all, it's the empty set. These are the three single element subsets. These are the three double element subsets. This is the one triple element subset. And if you add all these sets together to see how many there are 8, and our book does a pretty good job of telling us if you have a 3-element set, then there will be 2 to the 3rd power subsets. If you have a 4-element set, there would be 2 to the 4th power subsets. If you have a 5-element set, then there would be 2 to the 5th power subsets. There are all kinds of patterns going on here. There's something called Pascal's triangle, which some of you may recognize from other math classes. And in Pascal's triangle, any two numbers next to each other added together give the number in between underneath. So 2 plus 1 is 3. 3 plus 3 is 6. 1 plus 3 is 4. And notice these numbers, 1, 3, 3, 1, are a row in Pascal's triangle, and that will be true always. So there's just a richness of patterns here that we really don't have the time to go into, and I wish that we did, but there's a lot of patterns there, an awful lot. Since our book uses this idea of how to know the number of subsets in a set, it's 2 to the power, and that power is the number of elements in the set, I thought that I might outline a proof. So we have listed here previously the subsets of the set ABC. These are the 8 subsets. And we know that if there's a 4-element set like this set, there should be 2 to the 4th power, or 16. It should be twice as many as 8. And I want to give you the outline of a proof of why it would be twice as many. It's pretty simple. There's lots of proofs actually. But this particular proof says that the subsets here, which are going to be 16 of them, will be these subsets. Every single one of these is a subset of this. Plus, and then these subsets with a D inserted in each. So for instance, for this second part, the first part you just copy down the 8 subsets we already have. For the second part, instead of copying down this empty set, it would be an empty set with a D in it. That would be a D. And here, instead of A, B, and C, we'd have A, D, B, D, C, D. Here we'd have, instead of AB, ABD, ACD, BCD, and here we would have ABCD. So we'd have the 8 original, and we'd have 8 more with a D added in, and together that will be all of them. You can check it out by listing them, but that's all of them. And so every time you go from like 3 element sets to 4 element sets, or 4 element sets to 5 element sets, it always doubles, because you get a copy of the original plus another copy of the original with 1 letter added on. I wanted to mention the counting principle here. When we're counting up elements of sets, sometimes people wonder, what about more realistic problems where there's more than just a choice of having something or not having it, kind of a binary choice of 2 different possibilities. And so let's say that a person has available these types of clothes. Now, of course, this person really likes shoes with 100 pairs of shoes, but oh well. And let's furthermore stipulate that when they choose an outfit, they're choosing one of each of these. They don't have the choice of wearing no outfit at all. So the counting principle says if there's 7 ways to choose one thing, and 5 ways to choose another, and 4 ways to choose another, and 100 ways to choose another, and 3 ways to choose another, that if you multiply all those together, you will get the total number of different possible combinations. In other words, in this case, the total number of different outfits. And so when we do that, I think we see here that we get 20 times 7 is 140, times 3 is 420, times 100 would tack a couple zeros. So I think if you grab a calculator, there would be 42,000 different possible outfits that this person could wear. Now, some of them might not look very good, but that's a different topic for a different day. So this counting principle comes up a lot, and it is more general than our work with sets. In sets, what you have is, you often have a choice. You're either going to add on something to your salad or not, and that's a choice of 2 things, and add on this or not, and that's a choice of 2 things, and add on some of this or not, and that's a choice of 2 things. And so when we're working with sets, there's always this kind of either it's in there or it's not, and that's why we can calculate the number of elements of a set, the number of subsets of a set, by taking 2 to the number of elements.